So with collisions, there's two different types of collisions that we can look at. First is an elastic collision. In an elastic collision, a big key is that the two objects don't stick together after the collision. But even more important is that there is no loss of kinetic energy during the collision. So if we were to measure kinetic energy before, it would be equal to kinetic energy after the collision. And that's a very important thing, and it's actually going to help us solve a lot of problems. So let's look at this problem. We have a 0.5 kilogram object initially moving at 4 meters per second, collides with a 3.5 kilogram object that is initially at rest. And we want to know how fast they're moving after the collision. So we know we have an elastic collision because they're not sticking together. So m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. So there's our conservation of momentum, right? We have our velocities before and after, we have our masses, and then we also know that kinetic energy is conserved. So 1/2 m1v1 squared plus 1/2 m2v2 squared equals 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared. And so there's our conservation of kinetic energy. And since I don't know any of the velocities afterwards, I'm going to have to use two equations because I have two variables. I have v1 prime and v2 prime. So the first thing we're going to do is we're going to rewrite our momentum equation here. So we have mass 1 and mass 1 and mass 2 and mass 2. So we're going to kind of combine mass 1 on one side and mass 2's on the other. And when we do that, I'm not going to go through every single step here, but we end up with something like this. We have mass 1 times v1 minus v1 prime, and that's going to equal mass 2 times v2 prime minus v2. And then we can also do a very similar thing with our kinetic energy, right? We have a half in every term, so the halves can disappear. And then we're going to set it up the same sort of way, where we have m1 times v1 squared minus v1 prime squared equals m2 times v2 prime squared minus v2 squared. And then we have to think back to some nice little algebra tricks here, and know that if I were to do, say, something like a1 minus, or a minus b, and then b minus a, that would actually give me a squared minus b squared. And then we can kind of use that to factor this out and say that instead of writing this stuff, we can write m1 times v1 minus v1 prime times v1 plus v1 prime. And I just realized I wrote these wrong here. This should be a plus here. Okay. And then equals on the other side m2 times v2 minus v2 prime times v2 plus v2. Or actually, got my primes backwards here. v2 prime, v2 minus v2. So we have those all set up, and what we're going to do is actually take this equation, so we're going to ignore this piece here, and we're going to divide that equation and that equation. Or my momentum, I'm going to take that divided by my kinetic energy, and what you see happen is that some variables are going to cancel out, and I'm not going to spend a ton of time going through the algebra here, but what we end up with is that v1 plus v1 prime equals v2 plus v2 prime. And we usually kind of rewrite this equation just so that things are a little bit easier when it comes to solving problems. And we say v1 minus v2, so there's our initial conditions on one side, equal negative v1 prime minus v2 prime. And this is an equation that we can use in sort of any circumstance to figure out problems where we don't know velocities after a collision. So I'm not going to go through and solve this problem out completely because it'll take more time than you want to spend watching this video. But essentially, this V2 is 0 since our object is at rest. So we have V1, we have a number there, 4 meters per second, and then in terms of these two. So we can solve for either V1 prime or V2 prime and substitute it into our equation up here, and then we would only have one variable, and we could solve the problem and then do the rest. So after feeling completely overwhelmed with elastic collisions, we arrive at inelastic collisions, and these are much simpler, luckily for us. These are where two objects stick together, and kinetic energy, more importantly, is not conserved. So even in an ideal situation where we wouldn't lose energy to friction or anything like that, just the act of making two things collide and stick together, even if it's for a brief period of time, causes us to lose kinetic energy. It takes energy to make that stick happen. So if you look at our equation, we could say that m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime, and those would be our equations for conservation of momentum. But in this case, our m1 and m2 stick together and have the same velocity after the collision. So we could actually rewrite it to say m1 v1 plus m2 v2 equals my total momentum after, which would be the total mass. And actually, we could even rewrite that to make more sense here and say m1 plus m2 times their combined velocity together of v prime. And we could use that equation to solve our inelastic collision problems. And that's really all we need, because kinetic energy is not conserved and we don't know anything about it. Usually in the problem, we're stuck with that, and they move at the same speed afterwards, so we don't run into that same issue in the previous problem where we didn't know any of the velocities afterwards. So to solve this sample problem here, we have things moving in different directions. So this is an example of a problem in elastic collision in multiple dimensions. So what I'm going to do is I'm going to look at both the x direction and the y direction in my attempt to solve this problem. Well, in the x direction, I have momentum 1. Well, let's just cut down to it and say mass of object 1, velocity of object 1, plus mass of object 2, velocity of object 2, equals mass of object 1, velocity of object 1, mass 2, velocity 2. And this is all in the x direction. Well, object 2 is initially at rest. So we're solving for v2. Right, we want to know how fast it's going, and part of that is going to be in the x direction. So my v2 in the x direction would be m1 v1. Oops, I forgot my primes here, I just realized. Minus m1 v1 prime divided by m2. So if we plug in our values here, we could factor out an m and say 0.250 kilograms times my change in velocity, which would be going from 2 meters per second, was v1, minus v1 prime. Well, don't forget that we're at a 45-degree angle now. And so in my x direction, it's actually going to be the cosine of that. So instead of being the 1.50 meters per second, it's going to be 1.50 meters per second times the cosine of 45 degrees to pull out just the x component of that, divided by my mass of object 2, which is 0.400 kilograms, and velocity 2, and remember this is just in the x direction, prime, is equal to 1.32 meters per second. And then in the y direction, when we look at our conservation momentum there, well, nothing's moving in the y direction to start. Everything's in the x direction. And then m1 v1 prime plus m2 v2 prime. So v2 prime is going to be equal to m1 v1 prime over m2. And again, we're going to have to consider direction here. So it's m1, my 0.25 kilograms, times my 1.50 meters per second. And this time, instead of the cosine, it's going to be the sine of 45 degrees, divided by 0.400 kilograms. So V2 in the y direction would equal 0.663 meters per second. And now, something to kind of keep in mind here, I kind of just flipped through the algebra here. We should probably put a negative here to indicate that those are moving in the opposite direction. And so now, kind of my final answer, I put the two pieces together, and I say that, well, it's moving 1.32 meters per second this way, and then it's moving this way at 0.663 meters per second. And then find my total velocity and my angle, which I'm going to leave you guys to do. So you can kind of see the vector nature of how things work out when we're doing in multiple dimensions. So you just do Pythagorean theorem, get the hypotenuse, and then maybe an inverse tangent to get the angle.